Hello my friends and welcome to SciNick. Today we're going to be looking at the topic of electricity from Physics Paper 1 in AQA. So we're going to look at the symbols, we'll look at how current works and definition of it, we'll look at potential difference, how they fit together in something called Ohm's law. We'll then explore how resistors work, looking at them and current and voltage in series and parallel. We'll look at how electricity is used domestically, so in our own homes, what voltage we use, frequency, how a plug works. We'll again look at power, which we've seen before in energy, in the energy topic. We'll look at how it's used in appliances. We'll move on then to looking at the national grid and finally the physics-only part of static. So the first part of the electricity topic that we need to really know are the circuit symbols, because the circuit symbols allow us to explore circuits and how voltage and current and resistance work in those circuits a bit more. The easiest ones perhaps to look at are just a switch, so a closed and an open switch. Obviously with the open switch we have a gap in the circuit. Breaking the circuit wouldn't allow current to flow, so there would be the circuit would not work, so the circuit would in effect be turned off. The next two that are linked are cells and batteries, and you can see that a battery is made up of more than one cell put together. A battery symbol that we have there is often used to represent a power supply as well. It's unlikely that you would ever use just one cell, because even batteries that we use are multiple cells put together. But the idea there is we have a positive end and a negative end. The positive end, as you'll see, is the longer end. And I always imagine that if you break that in half, you could actually split those into two twigs to make a plus sign, compared to the small side, which is only the length of just one of those twigs, which would only make a minus sign. My mind works in weird ways sometimes. Anyway, the next part is a diode, and a diode again has a lovely little part to it, which is an arrow. And that arrow shows us that the electricity will only flow in one direction. So that's what a diode will do. It will basically allow electricity in one direction, or current to flow in one direction, and it will have a very high resistance in the other direction, which basically means current will not flow that way. So it can be used in limiting the movement of electricity in certain directions. It's used in quite a lot of computer components. The next we have here is a resistor, and a resistor is obviously key in restricting the flow of current. We use this symbol, so a kind of box in between the wires, and you'll see that there are a couple more that then use that kind of structure. So a variable resistor has an arrow through it, meaning that we can change the resistance of that resistor. The resistor above that we've just seen here is a fixed resistor, so it's got a certain value of ohms of resistance it applies. But the variable resistor is usually has a knob or something that you can twist on it, or you can vary the length of wire that you're using, for example, which will change its resistance. Linked to that we have the thermistor, and the thermistor again is a resistor which is dependent on temperature, and an LDR, which is a light dependent resistor, which again you've got your resistor symbol in there, surrounded by a circle with arrows coming in to represent the light or energy coming in to this component. And again, so its resistance is dependent on the light that it is exposed to. Fuse is the only one that has then a similar structure. Fuse has got this little tiny line running through the middle of it, which is representing the wire within a fuse that would melt if there's too much current. In effect, that's what a fuse is. It just needs to get hot and it will stop working. The remaining symbols we have an LED, so again that's a light emitting diode, and that diode has that arrow symbol to it again, so it's only going to allow electricity to flow in one direction through it, and it also has these little arrows coming out of it showing that we're removing something or giving off something, and in this case this diode is going to give off light. Similarly, the lamp will give off light, but it doesn't have arrows coming off of it. You can figure it out and tell me, I'd be very happy to know, but the lamp symbol has a cross through it. That's the way that the AQA are provide it to us, but we're also you might see in other websites that a lamp can have this symbol too, but the one that AQA needs us to know is the cross through the circle. And voltmeter, probably the easiest to recognize. You've got a nice big V inside a circle, and an ammeter measuring amps. Measuring the current is going to be a capital A. So on to what electricity really is. So electricity depends really on three things. So it depends on current, it depends on the voltage or potential difference, and it relies on resistance to allow those things to kind of work and do work. And the first part we're going to look at and consider is something called current. So current is the rate of flow of charge, and this will come up in your chemistry too. So in chemistry, you'll look at a flow of charge through ions in electrolysis, for example, or chemical cells. But in physics, we're mostly looking at the idea of the flow of electrons. But when you're defining current, you must say charge. It's not just electrons, but electrons in this case are important. So in a metal, it will be electrons that are traveling, because metals have delocalized electrons which can move freely. But to get us to have a flow of current, there must be a source of potential difference. So for example, if you have a cell, the cell has a positive end and a negative end. And what the electrons will do, electrons are negative, and they will flow round from the negative end to the positive end. Okay, that's the actual way. That's the true direction of current. However, conventionally, before we really understood what current was and how electrons flowed, we said that electricity flowed from a positive to a negative direction, which was conventional. That's a conventional direction of current. And you'll need to be aware of that, because in magnetism, we need to know the direction of current flow is the conventional way. But in true flow of electrons, the actual way that it flows is from a negative to a positive. They are negatively charged, they are attracted to the positive region, or the more positive region compared to the more negative region. For current, we do need to know an equation, and the equation actually is a definition of what current is. So if current is a rate of flow of charge, we can say current, which is a letter I, which is measured in amps, which I love because it's got nothing to do with current. There's no C or anything involved here. So current is a letter I measured in amps, is equal to the rate of flow of charge. So if it's a rate of flow of charge, as I've said in previous videos, the fact that it's a rate means we have to be dividing it by time. It's something per second. So it's a rate of flow of charge. In this case, it's charge, and we give charge the letter Q, which is measured in coulombs, C, and time is measured in seconds, so we must be converting any minutes that you might have into seconds. And that's our definition. So we have a definition of current is charge per second, passing a single point per second. How many electrons or ions are passing a point every second? That is our current. If we have a higher rate of flow, we have a higher current. And the second part that we need to understand at this point for current is that if we have a very simple circuit of delivery of current to a lamp, so there's our cell, it's going to be delivering in a negative to a positive region, negative to positive direction like this, in a single closed loop. So this is a singular closed loop. It's only travelling around one way. There's no other path it can travel on. At any point on this circuit, the current will be exactly the same. The rate of flow of electrons or charge around the circuit at any point there is going to be exactly the same. Before and after that lamp, exactly the same. So just need to make sure that we know this equation. This is one that we have to know, we're not given. The next part to electricity and understanding how it works is understanding something called potential difference, or the voltage. And the voltage is basically the difference in charge in two regions. So as we saw earlier, we have for a cell a positive region and a negative region. The potential difference is a difference in energy in these two areas, if you like, the difference in potential that they have. So voltage or potential difference, you can refer to this term with either way. So potential difference or voltage, you're not going to get marked down, marked negatively for it. And voltage is the energy carried per charge. So again, that's our definition of what voltage is. So if current was the rate of flow of charge, voltage is how much energy each of these bits of charge are delivering. So it's also how much the power supply is adding to them, and it's also then how much energy each bit of charge is delivering. And with that, we can actually define voltage with an equation too. So voltage is equal to the energy per charge, energy over charge. So charge again being in coulombs, energy being in joules, and voltage or potential difference is conveniently in volts. The relationship between current, voltage and resistance is that the current flowing in a circuit depends on both the resistance and the potential difference. So if we have the idea of current, we have resistance and we have voltage. If we increase the voltage, we are going to increase the current, because increasing the voltage gives more of a difference between our positive and our negative regions. So with our cell here, we're going to increase the difference here, so we're going to encourage more movement of electrons or ions, so more movement of charge, higher rate of flow, therefore more current. If we decrease the voltage, you're going to decrease the current, because there's less push, there's less attraction, there's less movement potential, if you like. However, if we increase the resistance is a restriction of a flow of charge. So it's making it harder for current to move. So if you increase the resistance, you're going to decrease the current. If you decrease the resistance, you'll increase the current. So these two factors are both going to affect how current moves. And actually we can turn this into a law, and this is maybe a law that you've investigated, because you should have, it's a required practical. And the relationship that you would have come up with is something called Ohm's law. And Ohm's law is defined by an equation. It's a relationship between voltage, current and resistance, and this is how you should learn it. But really for the current's sake, it should be I equals V over R, where if you increase the resistance, if this goes up, your current's going to go down. If you increase your voltage, your current's going to go up. So I can hear you thinking, how do we do this Ohm's law investigation? How do we set it up? Well, in essence, it was quite simple. What you had to do was you had to have a length of wire that you could vary the length of. So you have a range of lengths of wire. And this, of course, is your independent variable. It's the thing that you're changing. What you also then had to have was a variable resistor, so that you could find the appropriate amount of current that you wanted flowing through that wire, so that it didn't get too hot, and so that you got enough readings, got a good enough range of readings too. The second thing you needed to do was to record the voltage and the current running through this wire. So to do that, we had to put in an ammeter and a voltmeter, but these two both go in a different location in a circuit to take readings. So if we want to take a reading of the current, we have to take a reading from the loop the current is going to be mainly flowing through. So we have to take it actually in the series circuit itself. So we actually stick it in that loop, and we just plonk it right in the middle. We have the electricity flowing in one end and out the other. We take readings from that. So that's our current. We then also need to put in a voltmeter, but a voltmeter, remember, measures the potential difference. So it looks at what the difference in energy on charge is here compared to here. So it's almost like how much energy has been lost in this region of the actual wire itself. And that wire is going to get hot. It will have quite a high resistance compared to the rest of the circuit, because it's a long length of wire, so it'll be losing energy. It'll be restricting the flow of current and losing some of the energy as a result. So the charge will have less energy afterwards than it will before. So we should see a potential difference there. So what you would have done is recorded the current and voltage of a range of different wire lengths. So you might have 5, let's call it 0.5 actually, 0.1, 0.15, regular intervals. You get a reading of your current, get a reading of your voltage, and what we can do with that is then work out the resistance in total. So if we imagine we've got a constant voltage being put out by this power supply, let's call it 6. So we've got 6 volts, which is not going to change. The amount of volts being supplied and being used up at this fixed length or range of length of wires should be exactly the same, because we're not changing how much power is being put in, or the voltage being put in, sorry. What is changing though is as you change the length of this wire, charge has to move through more metal ions. So as a result, what we should see is that the current should decrease. So let's say it starts off being really high. This is all hypothetical, of course. It starts off being 6, goes down to 3, goes down to 1. The resistance, on the other hand, would be increasing. So if our current is being restricted, it's increasing like that. I mean, these are just hypothetical results, not necessarily going to fit the pattern, but the point is the same. The voltage in here, the total voltage, should always be equal to the current times by the resistance. So R being 1, I being 6, 6 times by 1 gives us 6 volts. 3 times by 2 gives us 6 volts. 1 times by 6 gives us 6 volts. So if we're going to increase the resistance, the current must by decrease. It's called an inverse proportionality. Here in this setup, we can vary the length of wire. We can also vary the resistance of the variable resistor to change the current running through that wire if we wanted to. So there's a few things we could change. But of course, remember that if you're going to be doing an investigation, you should only really change one variable as an independent variable at a time, that is, controlling the others. What we can also make a note of here, because it's a required practical, are the safety precautions. And if this wire is going to have a high resistance, it's going to be releasing a lot of energy as heat, so you must make sure that you turn it off after you've done the test. You've got your readings, just turn off the circuit straight away, change what you need to. If you want to take another reading, turn it back on again, but only have it on to take readings themselves. And obviously before you then touch it, you can make sure that you turn off the circuit, let it cool down properly before you pack it away. Following on from understanding how voltage, current and resistance work, we should be aware of how the resistances of certain different components will behave when you change the current or voltage in a circuit. So this is a required practical, and what we do here is we have a little setup of our circuit diagram. If you look here, similar to before, where we have a power supply or a battery, we have a ammeter to record current, and we have a voltmeter to current volts to record the volts, and we have a variable resistor so that we can vary how much current is running through the circuit and therefore investigate how the voltage and current behave as we change it. So what you could do here is, in this little gap, you could add in your lamp, you can add in your resistor, whatever it is you want to put in there. Okay, now what you would get then is a set of results which you then should compare. And in this comparison, you have a graph here which has a positive as well as a negative end. So we've got a positive and negative on the y and a positive and a negative on the x, and that's really important because we might change the direction of the current through this component, and that's quite important. So for the first example here, we've got the ohmic conductor. So this is just a fixed resistor. So for this resistor is actually, the resistance will remain constant. So if we increase the voltage from 0, the current will increase by the same amount every time. So as the voltage doubles, the current should double too, and that's called directly proportional. So this kind of graph here is directly proportional, especially because it also goes through 0. So sometimes you have to define that actually. Defining directly proportional is where as you double voltage, the current will double too, and it passes through 0. But if we then put the ohmic conductor the other way around, so the resistor the other way around, so we flipped it, you'd have exactly the same pattern. So even if you had it running through, current running through it in a negative direction, the relationship between current and voltage would be exactly the same. It's still directly proportional. But that is only if the temperature of that wire or the resistor remains constant. Because if you increase the resistance of these the chunks of metal, really, the particles in that metal will vibrate more, and it makes it more difficult for the electrons to move through that metal bit of wire. And if it makes it more difficult for those electrons to move through it, you're increasing the resistance. The next component we're going to look at here is a lamp, and a lamp is quite similar to a resistor, the ohmic conductor, in its first part of how it behaves. So if you increase the voltage and current to a point, it's following that same directly proportional rule. But the thing about how a lamp works is the wire inside the lamp is just a filament, really, which gets very hot. And as it gets hot, it releases enough energy, it releases so much energy that it's producing light. And that light is released because of a high temperature. And if it's a high temperature, we know the resistance is going to increase. So if there's an increase in the temperature and there's an increase in the resistance, there's going to be a decrease in the current because less current can flow through, less charge can flow through. So as a result, we end up seeing kind of tailing off in our graph, and it ends up being more like a kind of S-shaped graph, because that happens exactly the same at the other end in the negative region. So we have this kind of curving shape to the top end of this graph. So directly proportional for the first part, and then it kind of plateaus on the second part where the resistance has got higher, and so the current will stop increasing, or increase by less to the point at which it will stop increasing. The third component we'll look at here is the diode, and the diode, as we saw earlier, behaves in a particular way that will only let current flow in one direction, and that current is running in the positive direction. So if we run it in the negative direction, there's a very high resistance and the current will be basically zero. So if we have the voltage increasing, it should stay pretty much at zero. It's not perfect there, but it should be pretty much at zero, just above zero if anything. But if you're running it in the positive direction, when we have enough voltage, it will start having a lovely straight line coming up. So from there it would go on kind of in this way, in an almost directly proportional kind of way. For the fourth and fifth components, we don't need to look at a relationship between voltage and current. We need to look at their relationship with the environmental variable that affects them. So for a thermistor, it's the temperature that changes which affects its resistance. So what you can do here, rather than looking at voltage and current, you can have temperature and resistance. So if we increase the temperature here for a thermistor, the resistance will decrease. So if we have a low temperature, the resistance will be high, and if we increase the temperature, its resistance gets lower. So you have this kind of curve-shaped graph. Now this can be useful in things like a thermostat. So a thermostat regulates the temperature in a house or a building. As the temperature gets down to a certain point, its resistance will increase. And once it's increased beyond the threshold that you've set on your thermostat, it will switch on. And for the final component is the LDR, the light-dependent resistor. And the light-dependent resistor, again, we're looking at the variable of light compared to resistance. And it has the same pattern as a thermistor. So as the resistance decreases, the light intensity increases. So if we have our resistance starting high, it works its way down. It's the same kind of graph shape. So our light getting higher in this direction, resistance is getting lower. And this can be really useful, for example, in switching on lights when it gets dark. So again, once our light is in past a certain threshold, the resistance is going to increase to a certain point, and the circuit will cause lights to then turn on. Clever systems. Now that we've looked at how different components behave, let's look at how different circuit layouts will behave. So we have two different types of circuit layout. First is a series circuit, and the second is a parallel circuit. Now a series circuit is where we have basically one single loop where the current doesn't have any alternative pathway available, if you like. So if you look at these two lamps, they are in series with each other. The electrons will flow from into one and then into the other, and then back to the power supply. In a parallel circuit, the current will have an option of travelling down one of two pathways, or even more than that. So they are in parallel with each other. You can see that each one is in their own individual loop where the electrons will travel through. Now, these different setups will mean that the current potential difference and resistance will behave differently according to whether they are in series or parallel. So let's talk about how these rules will work. So current in a series circuit will be exactly the same at any point around it. Now, for example here, if you look at the circuit we have drawn out, at point 1, 2, or 3, you'll have exactly the same number of electrons moving around at the same rate, and so the current will be the same. However, when it comes to the parallel circuit, if we've got point 1, 2, and 3, at point 1, we've got all the current flowing through the circuit. When it gets to this branch point, the current can move one of two ways. So it will split. The split is not always even, but the sum total of 2 and 3 will be equal to what was supplied at number 1. So that current is split according to that loop's total resistance. But as we say, the total current in the second and third loops are exactly the same. The sum total of those is exactly the same as point 1. For potential difference, the voltage is shared across each component. each component in that loop. So for the two bulbs we have here, if we imagine that we've got, let's say 12 volts being supplied, if they were the same strength light bulb, if you like, they would each have 6 volts. So the supplied voltage is being shared across each component. However, for the parallel circuit, if we have 12 volts supplied from the power supply, each of these light bulbs will also get 12 volts. So actually the voltage supplied is the same in each loop. So the energy being delivered by each charge, going back to our definition of voltage, is exactly the same in each of these loops. There's nothing different about how much energy each bit of charge is going to have. They're just going to have less charge being delivered. So actually the energy they're receiving is exactly the same as that being supplied. So these bulbs in the parallel circuit are actually going to be much brighter than in the series circuit because they're getting much more energy per charge. But as I say, that delivery of charge per second is going to be smaller because it's split from each pathway. So the definition there for potential difference in parallel, the potential difference is the same in each loop. So far the current is the same at any point in the series circuit, but the potential difference is shared across each component, whereas for the parallel, the current is shared between loops, but the potential difference is the same in each loop. And the final little bit is resistance. So when we have resistors or components in series, they follow a rule, which is one that we do need to know. It's a little equation, which is RT, the total resistance in that series part, is the total of resistor 1 plus the resistance of resistor 2 plus resistance of resistor 3, and so on. So if you have 3 resistors in a line, first is 3 ohms, second is 2 ohms, third is 1 ohm. The total resistance, if you add them all up, is going to be 6 ohms. Each one in a line next to each other is going to add to more resistance of that series loop that the current has to move through. So every time it moves through one of these resistors, the rate of the flow of the charge is going to be reduced, and so there's more resistance, and as a result there'll be less current. But when it comes to a parallel circuit, what we're actually doing is providing an alternative pathway for our current to move through. So if we're adding more resistors, if we're adding an extra resistor in parallel, we're actually adding an extra option for current to move through. So we're actually making it easier. Now, a model of modelling how current works is by imagining these as being pipes of water, and a resistor is a thin section in the pipe of water. Well, if you're adding another thin section of water, overall you've added more space for the water to move through. So we've actually added more space for electrons or charge to move through. And so the sum total of R ends up being less than the smallest resistor, because we've added in more pathway for the charge to move through. So adding a resistor in parallel actually reduces the overall resistance of this circuit. So as an example here, we have a series circuit which is set up where we're given 3 locations of ammeters. We're given 2 locators of voltmeters across 2 different lamps, and the supply voltage from the power supply, the resistance of the first lamp, the resistance of the second lamp, and we can calculate a few things of this if we have certain bits of information. So if we start off with current, we should know that in a series circuit, the current is going to be the same at any point. So it should be the same whether it's at A1, should be at ammeter number 1, ammeter number 2, ammeter number 3, the current will be the same. So at A2 we can put here, the current is going to be 4 amps. It would be the same at A3 as well. The rule that we know for voltage is that the volts in a series circuit are shared between each component, and if we add those together, if we sum those up, add them together, we should get the total, which is the supply. So the volts of 4 plus the volts of 6, that's a message from me as well, should be 10 volts. We can also do the same with resistance. So if we have resistor number 1 here has 1 ohm, I've calculated that myself because I know that the current at the first lamp is 4 amps and the voltage at the first lamp is 4 amps. And we've got an equation that we can use, V equals IR. And if we rearrange that equation, we get R equals V over I. And I've just done my voltage is 4, divided by the current, which is 4, gives me 1 ohm. At the second lamp, we can do exactly the same. So R equals V over I is equal to V, which is 6, divided by 4, which is equal to 1.5 ohms. So you can see that one's got a slightly higher voltage, but the same current running through it. The higher resistance means that we've got a higher amount of energy being removed from the charge. And the final little question that we can solve here for RT, the total resistance, remember that RT is equal to R1 plus R2, blah, 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 blah. Here we've only got 2 resistors, so if we add up the total resistance there, we've got a resistor of 1 ohm and a resistor of 1.5 ohms. That makes us RT equals 2.5 ohms. They won't ask you to do all of this in the same question, but they might ask you to do individual steps, which give you 2 or 3 marks each collection, which leads us to having wonderful, happy time getting good marks and good grades. So in the use of electricity at homes or domestic use, we have electricity in the UK delivered at 230 volts and 50 hertz. Now you need to know those numbers. 230 volts is obviously the power supplied, but the 50 hertz is referring to how many times the voltage will oscillate between a positive and a negative value. So AC is alternating current, alternating where the current is alternating because the potential difference is also alternating. And if you had a graph of it, you'd have a positive and a negative, and it would kind of oscillate like this. So it's flipping and flopping between being positive and negative. And the number of times it does that per second is 50. So 50 hertz, 50 times per second. You'll look at this kind of graph and what frequency in hertz means a little bit more when you look at the waves topic in paper 2. The other type of delivery of current is direct current, which is where the voltage and current remain constantly positive. So straight line here in the graph comparatively to the oscillating in alternating current in AC. And that direct current comes from batteries, for example. Direct current is a lot less safe. So alternating current is safe. If you imagine your muscles with electricity will contract and therefore not be able to let go of things if it was under direct current. But with alternating current, 50 times a second it's oscillating, you have a brief gap where you can actually then move, hence the kind of feeling that you get if you were shocked by alternating current. Not that you've probably ever felt that, which is probably a good thing. But in our plugs we also have a lot of safety features too. The safety feature that's really important here is the earth wire. So you need to know the layout of a plug. So the earth is the one that's right in the middle. That earth pin, so this is your earth pin, the earth pin will stop the appliance becoming live by carrying current if there is a fault. And this has a 0 volt, so it's literally taking it to earth. It's allowing that electricity to dissipate really quick and easy. The other cables we have are the brown, which is the live wire. You'd think brown would be earth because earth is brown, but the brown cable is carrying 230 volts. So that is the really dangerous wire there. It's connected to the fuse. The fuse is there as a safety feature too. And if there is a high current suddenly going through the live wire, then the fuse will melt and break the circuit. You also could get a circuit breaker which does a similar feature, similar function. But in a plug, you have a fuse. The other wire, the neutral wire, I call it the blue-trul wire because it's blue. Anyway, that has a very low potential difference again. It's very close to the Earth's potential difference. It's just greater than 0. So when you have your full circuit made of your brown wire, your live, and your neutral wire, your blue-trul wire, you have a potential difference of near enough 230 volts. It delivers energy very quickly. So in the energy topic, we looked at how energy is defined, power is defined as energy divided by time. We also looked at how it can be defined as work done over time. And when we looked at work done, we said it could be due to a force being enacted upon something or current moving through a conductor. And that's work also being done. So in this case, we're looking at the idea that power is energy transferred over time. It's the rate of energy transferred over time. And we also know the definition of current, which is the rate of flow of charge. So it's the charge, Q, passing a point every second. And the definition of a voltage is the energy per charge. Now, it just so happens that if we interlink these two definitions of current and voltage, we multiply them together, is equal to the Q over T times by E over Q. Now, if you then think and screw your maths head on, you can actually then cancel out the Q's, and you're left with IV, current times by voltage, equals energy divided by time, which is equal to power. So it gives us an equation that we need to know here, which is P equals IV. Now, we don't need to know the derivation of things, you just need to know the equation, but that's where it comes from. Power is defined as energy divided by time, but if you multiply together current and potential difference or voltage, you get the same thing, you get power, which is really cool. So we have used this equation, P equals IV, before. We used it in the equation for the practical for calculating specific heat capacity. And in that we had an ammeter and a voltmeter around our filament immersion heater, which allowed us to work out how much energy it was using. We worked out the power of that item, and we worked out how long it was being used for. So we found out time, and all we needed to do was multiply the power and the time together, and it gave us how much energy that heater had used, which was important in the specific heat capacity equation. So a little bit of a link there that they might make. They're not going to ask you questions discretely about electricity and discretely about energy. They're going to link questions together. So the next part to this bit of power and an equation that we need to know as well is when you're given a circuit that doesn't have voltage, but you're given current and resistance, is how do we work out the power then? Well, you could use two equations. You could use your V equals IR equation and use that to work out the voltage from your resistance and your current, and then input that, or you could combine them together into one equation, because what we can do here is we can substitute the V in the P equals IV equation for IR. So if we do that, you end up with P equals I times by what was voltage, V, which we're now putting in as IR. So P equals I times by R. And if we simplify that, we end up with I squared R, which is another equation that we need to know. P equals I squared R. So just a quick note on how energy is used in appliances with electricity. We know power is the energy transferred over time, and as a result, if power is being used, so delivering current and voltage as we just saw, the energy that's transferred depends on the time, how long the appliance is switched on for. So that goes back to our energy equals power times time, which is a rearranged version of P equals E over T. So it's dependent on, so the power of your microwave, for example, might be 850 watts, but the amount of energy that it's using is going to be depending on how long you've used it for. And both a battery, which is direct current, or a mains alternating current, they both deliver power to whatever appliance it is. They're delivering current, which is charge, and the current is the charge per second or per time. And remember, the potential difference then is how much energy each of those bits of charge is delivering. So the battery and the mains alternating current, they're both taking electrons along to the component or the appliance where energy is then being transferred and used. And just a little note to remember that when a charge is flowing in a circuit, it's work that's being done. So we're having work done, energy transferred in effect. So looking at how we deliver electricity to our homes, we use something called the national grid, and that's a national grid of electric cables, power stations, transformers that allow us to have electricity delivered. So when you're asked what the national grid is, you can basically just say it is cables and transformers which link power stations to a consumer. That's what AQA want us to know. So you've got power stations which link to transformers. The transformers will step up the voltage to then take it to your national grid cables, These are then taking your electricity around the whole country. You have electricity coming from nuclear power stations in Scotland, technically, to down to the tips of Cornwall. But these cables then feed into transformers, which will be step-down transformers, bringing down the voltage to then deliver it to your home to be safe. So let's look at these transformers a bit more. So a step-up transformer will increase the potential difference. So we're going from a small voltage to a large voltage. Now, the consideration here is that the power is the same before and after. So power before is equal to the power after. Now, if we go back to our definition of power as being in a current and a voltage sense, we could say that the I times by the V before is equal to the I times by the V afterwards. So if we're increasing the voltage, if we're turning this up, and it's got to be equal on the other side of the equation or afterwards, then the current must be decreasing here when we've increased the voltage. So as a result of reducing the current, we have less heat loss, so less dissipation of heat, because we've got it facing less resistance, if you like. There are fewer electrons moving through the circuit, and as a result, fewer collisions per second of the electrons with the ions in the metal, and so less dissipation of heat, less heat loss. And if you have less heat loss, that means less cost for the consumer, for the people like us who have to pay for electricity. And a step-down transformer then at the homes is there to decrease the potential difference. So again, we're bringing it back down from the really high voltage that's in the national grid cables to then to increase the current again. And by doing that, the decreased voltage makes it safer to use in the home. The final section of this topic, and this is for physics only, is looking at static. And static is where we are rubbing two insulating materials together, so using friction, and it causes the transfer of negatively charged electrons from one to the other. Now what this will do is it cause the one that has actually gained electrons will become negatively charged, and the one that's losing electrons will become positively charged. That's wonderfully simple. Now, if you have two charged objects, now that doesn't necessarily mean you have to have the one that has gained electrons and lost electrons. It could just be that you have one of those in any other object. Relatively, one will be charged and the other will be the opposite charge. When you have those, they will exert a force on each other, and that force will either be a repulsion or an attraction, and that depends on the types of charge that they have. So opposites will attract and like charges will repel, and it's just like how magnets work. So a north to a north of magnets will repel, and a north to a south opposites will attract. And if these oppositely charged objects get close enough together, they may discharge, which is where the electrons will transfer from the negative to the positive, so the one that has the electrons to the one that doesn't, until it makes them equal. At that point, they won't have a charge compared to each other, so there won't be any force acting anymore. Now, if the voltage is high enough, the difference is high enough, and the gap is small enough, it might spark through the air, so the discharge will actually happen across air particles, and as that happens, the air particles will release energy as light and heat. Now, after these objects have gained charge, they end up having an electric field. That electric field will act in a certain direction, and the way that we draw this is that we draw, for a positive, arrows going away from the centre in all directions. Should be equal length. I'm just rushing this to get it done. And you have been asked in the past by AQA to draw these. If you notice, closer to the object, you'll have more lines in the closer proximity than further away. So as a result, the electric field is strongest closest to the object. For the negative, the lines are just coming in instead. So you draw your lines in all different angles to show that they are affecting it on all sides. The arrows actually represent what would happen to an object that was positively charged placed in that region. So if you placed a positively charged object here, it would be forced away in the direction of that arrow this way. If you placed a positively charged object here, it would get forced towards the negative object. So the second object in the field experiences a force. As the distance between the objects gets smaller, so they get closer together, the force that they would actually end up having exerted upon them would be greater. And that's the end of our electricity topic. Thank you very much for watching. This is SciNick. Please like and subscribe. Watch more of my videos.